Okay, so welcome to this next video, which will be in the playlist on the gastrointestinal tract, and also in the playlist on lipid metabolism. And in this video, what we're going to talk about is the digestion and also the absorption of fat molecules, or of lipids. Okay, so digestion and absorption of fats, basically. So, we're going to start this video by talking a little bit about the basic anatomy of the small intestine, because the small intestine is the main site for both the digestion of fats and also the absorption of fats. Okay, right, so we'll start off with the anatomy of the small intestine then. So, let's draw a picture. We'll start with the esophagus, then we'll go into the stomach, and then we'll go into the small intestine. And really, all this is supposed to highlight is the different portions of the small intestine and also their relationships to the pancreas. And I think we'll also try and show the liver on this drawing as well. Okay, right, we might not have actually left enough space for the liver, but never mind. Here's the esophagus. Here's the stomach here. Okay, the stomach will then end with the pyloric sphincter here, and then we'll go into the duodenum here, like so. Okay, which has this characteristic C shape here at its beginning. Okay, then the duodenum will go along like so. Okay, and then the duodenum will end, and you'll start the jejunum here. Okay, so here's the next portion of the small intestine, which is the jejunum. Okay, and then the final portion of the small intestine, after the jejunum has finished, which it will do around here, is the ileum. Okay, and the ileum will then go along to the ileocecal sphincter, and then it will empty into the cecum, and that will take it onwards to the colon. Right, so here's the small intestine, so let's colour in the different portions here. So, we said that this portion right back here, and I shouldn't have actually drawn that physical line, I should have just had it shown with colours, because there isn't like a physical barrier there. But this portion in pink here, this is the final portion of the small intestine, known as the ileum, or the ileum, however you want to pronounce that. Okay, then there's the middle portion of the small intestine, which I'll have in orange here. Okay, and this is known as the jejunum. Okay, so this is the jejunum, Jejunun, like so. Okay, so that's in orange. And then we've got the first portion of the small intestine, which is the portion just after the pylorus. Okay, so I'll bring this back down. So this portion here, which I'm now colouring in blue, this is going to be the duodenum. Okay, right. So, and between the stomach and the duodenum, you have this special sphincter called the pyloric sphincter. Okay, so I think I'll try and show the pyloric sphincter here in turquoise. So there's a thickening of the circular smooth muscle which surrounds the intestine/stomach, whichever one you want to view the pyloric sphincter as belonging to. And basically, this is capable of contracting so much that it can completely occlude the lumen and stop the flow of chyme from the stomach into the small intestine. And basically, chyme is just the name for the food bolus, which is moving from the stomach into the duodenum. Okay, so this here, this is the pyloric sphincter. Okay, sometimes just called the pylorus. Okay, and then we have the stomach, which we'll have in pink here. Okay, so this is the stomach. And then finally, leading into the stomach from the oral cavity is the esophagus up here. Okay, and I'm going to use the British English spelling of esophagus. Feel free to drop the silent O if you use the American English spelling of esophagus. Right, so I'll colour in the esophagus in bright green here. Okay, right, so there is the basic anatomy of the small intestine. We've got the duodenum here, the jejunum second, and then the ileum. Okay, now sitting within the C shape of the duodenum here is a very important structure which we'll come back to later. So I'm going to put this in now, okay? And this is the pancreas. Now I don't think we'll get the liver in because not without sort of hugely abusing our artistic license, okay? And making the liver far smaller than it should be represented. So I'll just colour in the pancreas here. Okay, right, so this is the pancreas here. Right, okay, so let's now turn our attention to what's actually going to happen with regards to the digestion and the absorption of fat. So, a little bit of fat digestion occurs within the stomach, but hardly any, basically. So we're going to ignore the tiny contribution of fat digestion which occurs within the stomach, and we're going to study fat digestion within the small intestine. Okay, so what's going to happen is fatty food stuff is going to come down into this first portion of the small intestine here, the duodenum. Okay, right. So, basically there's a problem at the moment, which is that the fatty molecules are all very, very hydrophobic. And we probably should just discuss the different types of fat that you're going to have within dietary foodstuff. Okay, so by far the most common form of fat that you're going to actually be consuming are triglycerides. Okay, and the longer name for triglycerides is to call them triacyl glycerols. Okay, and for short, triacyl glycerols are often abbreviated to TAGs for short, so tags. T for tri, A for acyl, G for glycerol, and then we'll put the S on the end, so triacyl glycerols or tags. Okay, now let's just draw a little cartoon of the structure of a triacyl glycerol. Okay, so basically they are based on the structure of glycerol. So the backbone for the entire structure is glycerol. Okay, and then basically you have attached to your glycerol molecule 3 long-chain carboxylic acids. So I'm going to use this picture here as my cartoon structure for a triacyl glycerol. Okay, so these orange horizontal lines here, these will represent my long-chain carboxylic acids, and here in green, this will represent my glycerol. So, in green here, this is my cartoon for glycerol. Now, the chemist's name for glycerol is to call it propane 1,2,3 triol. Okay, so propane 1,2,3 triol. And although propane 1,2,3 triol is a bit of a mouthful, it's a useful name because it tells us exactly what we're dealing with here. It tells us that we're dealing with a 3-carbon molecule which has alcohol groups coming off the first, the second, and the third carbons. Okay? And it has a single alcohol group coming off each of those carbons. Then, what we have esterified to the alcohol groups coming off the first, the second, and the third carbons, we have long-chain carboxylic acids. So basically, carboxylic acid groups can react with alcohol groups to form ester links, and this will attach these long-chain carboxylic acids to the glycerol backbone, basically. Now, long-chain carboxylic acids is the official name for what a biochemist would call fatty acids. Okay, so it just means a carboxylic acid molecule that has a really long tail, basically. And generally, they're going to have really long hydrophobic tails. So let me give you an example, for instance. So an example of a long-chain carboxylic acid is stearic acid, or stearic acid, however you want to pronounce it. And stearic acid, its official name, or its chemist's name, its new name, if you like, is octadecanoic acid. So stearic acid is the old biochemist name that is still commonly used. The more modern name, which makes better sense, is to call it octadecanoic acid. And the reason this is a better name is it tells you exactly what the structure of this molecule is. It tells you that we're dealing with an 18-carbon, fully saturated carboxylic acid. So here's our carboxylic acid head. Now we need the other 17 carbons, okay? 16 of those are going to be in the form of methylene groups, so I'll draw one methylene group, I'll bracket it, and then put subscript 16. That's a useful trick for getting out of having to draw 16 methylene groups, okay? And then finally, on the end, we then have a methyl group. Okay, so this is the structure of octadecanoic acid or stearic acid, and basically this is our sort of archetypal example of a long-chain carboxylic acid that you can esterify to glycerol molecules to produce a triacyl glycerol. Okay, and I should stress that the long-chain carboxylic acids which you put in all three positions don't need to be the same long-chain carboxylic acids. So you could have a stearic acid here and then something different in position 2 here. Okay, so basically triacyl glycerol is not a set molecule. You know, there's a huge number of different triacyl glycerols. It's a huge, great category of molecules which all have similar chemical properties. Okay, right, and the key chemical property that these triacyl glycerols have, in fact the key chemical properties that all fats, or the fancy word for fats is lipids, okay, so all lipid molecules have, is that they are incredibly hydrophobic, okay, so they don't interact very well with water molecules. Now the reason for this is that if you look at this structure here, the structure of stearic acid, you can see that it's very non-polar, okay? So even these bonds are not particularly polar. There aren't many dipoles here. The reason being that carbon and hydrogen have pretty much the same electronegativity, so the electrons are pretty much evenly spaced out. So this is a very sort of neutral molecule. Now, water molecules are the exact opposite of neutral, okay? Water molecules are very, very polar. Oxygen has a much greater electronegativity than the two hydrogen atoms, which means that the oxygen nucleus, which contains loads of protons, is much better at pulling electrons towards it than is the hydrogen nucleus. So the pull that the electrons in this covalent bond will feel towards the oxygen nucleus is much greater than the pull they will feel towards the hydrogen nucleus, and therefore they'll end up spending more of their time closer to the oxygen atom than they do to the hydrogen atoms. So basically this side of the molecule gets a partial negative charge, and this side of the molecule gets a partial positive charge. Okay, so it becomes very much so polar. Okay, this means that the water molecules can interact very nicely with other water molecules. For instance, if I bring another water molecule here, this side will be partially negatively charged, and this side will be partially positively charged. This oxygen will also have lone pairs of electrons, and these can interact beautifully with this partially positively charged hydrogen here in a very strong form of intermolecular bonding called hydrogen bonding. Okay, so basically water molecules can form very stable interactions with one another, whereas if I ram a water molecule next to this stearic acid molecule, the interactions it will form are frankly just ridiculously weak. They're van der Waals forces, or at the very best, they're dipole-induced dipole bonds. Okay, because when you bring the water molecule close to the stearic acid molecule, because water is partially charged, basically, so you have this polar structure, it will therefore make the electrons flee from it. So for instance, if I bring my water molecule, ram it against the stearic acid molecule, the oxygen has this partial negative charge, so that will cause the electrons close to, well, the electrons in the stearic acid molecule, which are close to where I have rammed this oxygen, they will flee from it basically, and that will create you a little bit of unequal distribution of charge. Okay, so that's called dipole-induced dipole bonding. Okay, because we have a permanent dipole within these water molecules. Okay, right, but that's still not very strong. Okay, so water molecules would much rather be interacting with each other rather than interacting with this, basically. So it's not thermodynamically favourable for water molecules to interact with stearic acid molecules. Okay, so that's what is meant by hydrophobic, that you have a very neutral, non-polar structure, and therefore you don't interact well with water molecules. Instead, what tends to happen is you get rammed in with other hydrophobic molecules. So what tends to happen is loads of hydrophobic molecules in a solution of water will all aggregate together so that they stay away from the water molecules, so that the water molecules can all interact with each other nice and favourably. Okay, right, so that's the main form of fats that you have within your diet. We now need to discuss a few more, because there are other forms of fats that will be present within your dietary intake. Okay, so triglycerides are one of them. Let's now talk about phosphoglycerolipids. Okay, so phosphoglycerolipids, it's a big word. Basically, these are the archetypal phospholipids. Okay, so whenever whenever someone says phospholipids, I can guarantee that you probably think in your mind about phosphoglycerolipids. Strictly speaking, phospholipids is a broader term than phosphoglycerolipids. Phospholipids covers a greater number of lipid molecules than phosphoglycerolipids, i.e. all phosphoglycerolipids are phospholipids, but not all phospholipids are phosphoglycerolipids. And we'll come back to that later. Okay, so let's now talk about phosphoglycerolipids. So basically, phosphoglycerolipids are all molecules which are based on the structure of a molecule called phosphatidic acid. Okay, so let me show you the structure of a phosphatidic acid molecule. So again, we'll use my cartoon. So I'll represent glycerol as a vertical green line. Okay, and that's why these are going to be called phosphoglycero. That's where the glycero comes in. They're based on glycerol again. Then you have two long-chain carboxylic acids esterified to the first two alcohol groups of your glycerol molecule. So these horizontal lines that are now being coloured in orange, those represent long-chain carboxylic acids. But then instead of binding carboxylic acids to these alcohol groups, instead of binding a carboxylic acid group to this third alcohol group, instead you bind a phosphate group to this third alcohol group down here. So this ball that I've now coloured in pink, this represents a phosphate group. Okay, now let me just discuss with you the structure of a phosphate group. So basically, the structure of an inorganic phosphate group looks like this. You have a phosphorus atom at the centre, with a double bond to an oxygen atom, then with two alcohol groups coming off the side of the phosphorus atom, and then a single bond to an oxygen atom, which then requires one extra electron to make up its 8 outer shell electrons, so it gains another by ionic means, and therefore ends up with a negative charge. Okay, so basically, you can bind phosphate groups to alcohol groups in much the same way as you can bind carboxylic acid groups to alcohol groups. So if, for instance, we have our alcohol group here, you can bind this phosphate group to this alcohol group. Now let me discuss with you how. Well, just look at this structure here. Forget about this and this down here. Just look at that portion that I've got here. If I replaced that phosphorus atom with a carbon atom, what would that look like? Now forget the fact that it's got 5 bonds, which is totally unrealistic for a carbon atom, but just look at this group that I've circled in pink. That would be a carboxylic acid group. So in fact, these phosphate groups have something very similar to a carboxylic acid group within their structure, except that instead of a carbon at the centre of the carboxylic acid group, you have a phosphorus atom. Okay, so basically, this carboxylic acid-like group can interact with alcohol groups in the same way that carboxylic acid groups can interact with them. Okay, so you can take off the alcohol group off the phosphate group. Okay, you can take the hydrogen off the alcohol group, and you can then bind the oxygen from the alcohol group to the phosphorus atom of the phosphate group. And this bond, which is very similar to an ester bond, is called a phosphoester bond. Okay, so this is a phosphoester bond or a phosphoester link. Okay, so basically this is how we are attaching phosphate groups onto this is how we're attaching a phosphate group onto that alcohol group coming off the third carbon of the glycerol molecule. Now, this structure that I have shown you here, this is what is known as a phosphatidic acid molecule. Okay, now once again, just like there was not one triacyl glycerol molecule, there is not just one phosphatidic acid molecule, because these two long-chain carboxylic acids that you have here are not set in stone. They can vary, so there are many different phosphatidic acid molecules. But to be honest, it doesn't really change the property of the molecule if you change the long-chain carboxylic acids. Okay, so it doesn't really affect us that much that these are variable. Okay, right, so phosphoglycerolipids, this term up here which we were apparently studying, these are molecules which are based on the structure of phosphatidic acid. So they're all effectively phosphatidic acid derivatives. Okay, now what do you do to the phosphatidic acid molecule to get some of these other phosphoglycerolipids? Okay, well basically what you're going to do is you're going to add extra things onto this phosphate group. So we have just bound the phosphate group to this alcohol group that comes off the third carbon of the glycerol molecule via this phosphoester link. However, even after you've got the phosphoester link established, look what we've got here. We've still got this phosphorus atom double bound to the oxygen there, and we've also got another alcohol group on the other side. Okay, so there's another alcohol group over here. Basically, if you look at this group that I have just circled in turquoise, and I understand that it's getting a little crowded here now, but just look at this group here. That just looks exactly like this group that is circled in pink, that has just reacted with an alcohol group. So basically, this can actually react with another alcohol group. Okay, so you can also form another phosphoester link using the other alcohol group of the of the phosphate group here. Okay, right, and that means that you can attach extra things onto the head of this phosphate group, and when you do that, you get a whole load of phosphatidic acid derivatives, and these are called the phosphoglycerolipids. Okay, right, so let me give you an example at least. So basically, one of the molecules that you can attach onto this phosphate group on the phosphatidic acid molecule is a molecule called codeine. Okay, so let me show you the structure of codeine. Now, this is the same codeine as is used in the famous neurotransmitter acetylcholine. Okay, so basically it's an alcohol. It needs to be an alcohol so it can react with this carboxylic acid-like group in our phosphate group. Okay, it then has two carbons, so here is an ethylene group. Okay, like so. And then off the other carbon over here you have a nitrogen atom which then has three methyl groups coming off it. 1, 2, 3. Now nitrogen doesn't generally form 4 bonds. It would like to have 3 bonds. Okay, so one of these bonds that the nitrogen has here must have been formed by the nitrogen putting both electrons into that bond. Okay, so the normal understanding of a covalent bond is that one electron comes from each of the members. So the nitrogen puts in an electron, the carbon puts in the electron, they then share this pair. Okay, so in this case, for one of these bonds, so let's say it's this one here, the nitrogen has put in both electrons. So basically it's as though the nitrogen has donated away one electron to the carbon, because as I say, the usual understanding is that one of those electrons in the covalent bond had come from the carbon. So if the nitrogen puts in both, it's as though one has been given away to the carbon. So that means that the nitrogen gains a positive charge. And you might say, well, surely then the carbon is going to gain a negative negative charge because it's received an electron? Well, the reality is that when this carbon initially came in to bind to the nitrogen, it would have had a positive charge. So when it gained the electron from the nitrogen, it was neutralized. So effectively, it's just deferred the positive charge onto the nitrogen. So the whole codeine molecule is actually positively charged. Right, so what you can then do is you can link the alcohol group of the codeine molecule to the remaining alcohol group of the phosphate group that is on the phosphatidic acid molecule. Okay, so this is going to get even more horrendous, but let me go with it. What you can then do is take the hydrogen off the alcohol group of the codeine molecule, take the alcohol group off that phosphate group, combine them together to make water, and then link this phosphorus atom here to this oxygen atom here of the codeine, okay, to create another phosphoester link. And you've then got codeine added onto your phosphatidic acid molecule. Okay, so the name for this then is phosphatidyl codeine. Okay, so phosphatidyl is the name for this group that we've got here, which is the phosphatidic acid group. Okay, and then we've got codeine attached to that, so it's phosphatidyl codeine. Now, sorry, I should have put the codeine there because actually, in fact, I will do that. These two words should be attached to one another. It should be one big word like that. Phosphatidyl codeine, and phosphatidyl codeine is often abbreviated to PC for phosphatidyl and then codeine. Right, so phosphatidyl codeine is an example of a phosphoglycerolipid, but there are other examples as well. For instance, phosphatidyl ethanolamine, phosphatidyl inositol 4,5-bisphosphate, phosphatidyl glycerol, to name just a few. Okay, and those will be present within the diet. Okay, not in as high a presence as the triacyl glycerols, but still in a presence. Okay, right, so we'll call it there for this video, and in the next video we'll continue our discussion of which lipids we will have within the diet with cholesterol esters.